Hi, ladies and gentlemen. We've previously discussed electromagnetism, and our next topic is going to be electromagnetic induction. Now, before we actually talk about electromagnetic induction, we first have to talk about what magnetic flux is. Now, magnetic flux is defined as the amount of magnetic field passing through a specific area. So it's very straightforward in terms of flux, which is represented by the Greek letter phi, where magnetic flux is equal to B times A. Okay, but this is actually a dot product, so there's actually a cosine theta there as well, which we're usually not going to use, but you should keep that in mind. So with flux, the unit for flux is going to be Tesla meters squared, or they sometimes also use Webers. Okay, but because Weber doesn't appear very often on the AP, we're going to stick with Tesla meters squared. And to give you a better idea what it actually means in terms of a magnetic field passing through a certain area.
When magnetic field lines pass through a flat surface, we can define a quantity called the magnetic flux that represents the number of field lines penetrating it. If the surface is rotated about the field lines, the magnetic flux does not change. However, the flux does change if the area changes. The flux also changes if the surface is tilted, falling to zero when the surface vector is perpendicular to the field lines. The cosine theta term in the equation accounts for this. When rotated past 90 degrees, the surface normal vector and the magnetic field vectors are in generally opposite directions.
Okay, so you can see that when it goes straight through, it's very straightforward. Cosine of 0 is 1. So in this first example over here, the area itself would be 10 centimeters squared, so 0.1 meters times 0.1 meters, which equals to 0.01 meters squared. The magnetic field is 10 teslas, so flux is B times A, so 10 times 0.01 would equal to 0.1 Tesla meters squared. Okay, so when it goes straight through, okay, the angle is always measured from the normal line. So in this case, the angle would be 0. Over here, we can see our normal line again, and this dotted line over here, and the angle in this case would be 20 degrees. So when we solve for the magnetic flux in this example, okay, we have to make sure that we include B times A times cosine theta to solve for the actual amount of magnetic flux. Okay, but the thing is, flux in itself was something that they had known about for a long time. It's simply the density of field lines. But Faraday noticed something very interesting. Okay, he noticed that a change in magnetic flux creates a current, or really a potential difference within any sort of loop that's passing through. If you take a look at this example over here, what I mean by a change in flux, okay, so here's a good example, okay, you can see, I'll pause it for a moment, that as the magnet moved closer, the overall flux that was passing through the loops over here is increasing. Okay, so when the magnet gets closer, the field lines there's more field lines passing through those loops, so the magnetic flux is increasing. And when it gets pulled away, we can see that there are less field lines now passing through the loops. So as the magnet was moving in this direction, the magnetic flux was decreasing. Okay? But what I want you guys to keep an eye on now, we'll run the simulation again, is look over here at the red arrows within that coil, okay? Because that represents the current. As the magnet gets closer, we can see the current in the loops moving in a certain direction, and when the magnet gets pulled away, it's moving back in the opposite direction. Now, why does this occur, though? Okay, so this is what we call this is also named Lenz's Law. Lenz's Law basically stated that the loop will oppose any change in magnetic flux. Okay? Meaning it literally is going to try to weaken it if it's getting too strong. So in this case over here, if we look at the first example, we know that there's a magnetic flux going to the right inside the loop that's being created by the magnet itself. But the thing is, the loop will try to oppose it. We know that in this case over here, the change in flux that's going to the right is increasing. Okay, so the loop will actually create its own magnetic flux to cancel it out. So within the loop, to cancel out the change. So in this case, if the loop is creating its own magnetic flux to cancel out the change, okay, that flux inside created by the loop goes left. So now if I use my hand rule, okay, so if I take a wire over here, okay, and we know that in this coil of wire, the magnetic field is going left. If I use my first hand rule, I'll make a note of that. Use the first hand rule to determine I direction. Okay? So in this case, if I use my hand rule, I know it's going to the left. I can see that as I wrap my right hand around it, my thumb is pointing upward on the side of the loop that's closer. So that's why over here we have these arrows that are all pointing up. If you don't, well, as a quick demonstration to prove that the magnetic coil does resist it, take a look at this example over here. In this demonstration, they first use an iron ball and they drop it through a copper pipe. And it falls normally. Took about 0.02 seconds. Now, they take a magnet, like a very strong neodymium magnet, and they drop it. And it took 4 seconds to fall through. That's because as the magnet is falling, if you were to actually take a look inside, okay, I'll just pause it for a moment. You can see it's taking its time to slowly fall down. That's because as it falls down the loop is trying to weaken the magnetic flux that's passing through. So it creates a magnetic field in the opposite direction. It creates a current. There's actually a current within the copper pipe, and there ends up, due to action-reaction, there ends up being a force acting on the magnet, which prevents it from falling down at the right speed. Now, if we take a look at the next scenario, though, okay, when we're pulling the magnet out of the loop, okay, in this case, when the magnet's being pulled out of the loop, the magnetic flux that was going to the right is getting weaker. It's decreasing. But as I said, the loop will oppose any sort of change. So in this case, there's a negative change in flux. So normally, well, I'll use red as I used red before. Normally, the magnetic field is going to the right, going into south, and that's created by the magnet itself. But it's getting weaker and weaker and weaker. So what the loop will actually try to do in this case, the loop will try to strengthen the flux that's going to the right. So it creates its own magnetic field going in the same direction. So whenever the flux is getting stronger, it will oppose it. Whenever it's getting weaker, it's going to try to help it out. So now, if we're looking at a magnetic field created by the loop, which is also to the right, okay, and if I look at my coil wire again, okay, so now, in this case, the magnetic field created by the loop itself is going right. So if I use my first hand rule again, and I can point my fingers inside to the right, I can see that my thumb is pointing straight down, which means that as it's being pulled out, there's a current going downward in the loop because of the change in flux. Okay? And if we have north, we would end up with something different. We would end up with the exact opposite happening. When we have north going back and forth, let's pause this for a moment. So north is going in. Okay. Now in this case, the flux is increasing again, but the magnetic flux that's going left is increasing. So we have a positive change in flux going left. So therefore, the loop is going to try to weaken that flux. It'll create its own flux in the opposite direction to cancel it out. So loop creates its own flux in the opposite direction, which is to the right. Which is why, if you observe it approaching again, if you use your hand rule, the current, as you can see, is going down. And when the north is pulled out, the current goes up on the side that's closest to us. Because as it's getting pulled out, okay, the flux is now getting weaker and weaker and weaker. So that means that the flux that was going to the left is weaker. So overall, we have a negative change in flux, which means that the loop is going to try to help strengthen it more. So to strengthen it, it will create a field in the same direction. And when it creates a field in the same direction, now if I use my hand rule to take a look at this loop over here, okay, so assume that I have a loop over here. If it's going to the left, you can see that my thumb is pointing up. If my thumb is pointing up, if you guys observe this pull away, you'll see that the current is going up as well, okay? And of course, it changes direction when it's approaching. Okay. So I just want you guys to understand that the magnetic field is always going to be opposite the change of flux. Okay? Okay. So now in this picture over here, this is another way of understanding what's going on. We have a bar magnet moving up, and we know that there's a magnetic field that's getting stronger and stronger. So that means the flux, in this case, that's upward, is increasing. The loop is going to try to create a magnetic flux that opposes this positive change in flux. So it's going to create its own magnetic field in the opposite direction. Okay? So now in this case, when I use my hand rule now, if I see that the magnetic field is going down, use my first hand rule, my thumb is pointing to the left when I grab on, because it's going in. So that means that overall, I have a clockwise current being produced. This example over here is the same problem as above, but it's just turned to look a little bit different. In this problem over here, they say the magnetic field is increasing with time, which means that the flux that's going out of the page is increasing. So the loop is going to try to weaken it by creating its own magnetic field into the page. So in this case over here, if I have a loop again, the magnetic field is going into the page being created by the loop. And again, you can see that my finger is pointing to the left. So over here, I still have a clockwise current produced, okay? Because it's the same problem as above, it's just from a different orientation. If that north magnet was being pulled away, so that means that the flux that's going upward is getting weaker. We have a negative change in flux. In this case, the loop is going to try to strengthen it and produce its own magnetic field. So in this case, over here, if it's coming out of the loop, okay, if it's coming out of the loop, we can see that my thumb is now pointing to the right when I use my first right hand rule, which means that a counterclockwise current is produced in this example. And for this bottom example over here, okay, again, the flux, in this case when the magnetic field is decreasing, the flux outward is decreasing, so I have a negative change in flux. So that means my loop will try to strengthen it by creating a field in the same direction. So if you were to use your hand rule, you would see that you still end up with a counterclockwise current. Okay? So it just takes a little practice, but in the end, it's not that difficult if you understand your hand rules. Now, so far, we've only dealt with situations where we have a changing magnetic field. But if you remember, our formula for flux was actually magnetic field times the area. So there's, besides changing the strength of the magnetic field, you could actually also change how much area is exposed to the magnetic field itself. So for example over here, if I took this loop and I were just to move it around, okay, when it's actually inside over here, okay, when it's moving around inside, there is no change in flux, because the fact is that the amount of B that's being produced and the area is the same. The only time there's a change in flux is when the loop first enters the field. When it's first entering the field, there is a positive increase in flux. And when it exits the field, there's going to be, over here, a negative change in flux. Because ultimately, once it exits the field, it's going to be 0. So that means that as it's entering the field, the flux strength is getting stronger. That means that the loop is going to try to resist it and create its own magnetic field in the opposite direction. So if you actually use your hand rule and it's coming out of the page, if you take your loop and you know that's coming out of the page, you can see that your thumb is going to be pointing to the right over here at the bottom, which means that we end up with counterclockwise current when the loop first enters the field. But now if I take that loop and exits the field, okay, we can see that there's a change in flux again. In this case, the loop is going to try to strengthen it. So if I use my hand rule, I can see that it's going to be going overall in a clockwise direction. Okay, and to prove that, of course, this does happen, I have another demonstration here by MIT, where they have a they have a magnetic field over here between these two plates. Okay, and they drop a loop through those plates. Let's take a look. Now, when they first drop it, you could see that overall, when it was being dropped, the change in flux, there's a positive change in flux here, resisted the fall. Over here, it fell normally, and at the end again, we have a negative change in flux. Okay, so because there's a negative change in flux, wherever there's a change in flux, we can see that there's going to be a resist. But if it's non-magnetic, it just falls through perfectly without having any issues. Okay. So if I go back to this picture over here, I just want you guys to understand that simply moving a loop in and out of magnetic field will create a change in flux. Another possibility is if you have a magnetic field and you again have that loop, but what if you were to take that loop, instead of moving it side to side, what if you were to actually rotate it? Meaning that if I took my loop over here and then rotated it to this direction, now overall, if the magnetic field is going into the page, how many of those magnetic field lines are actually passing through the loop? In this case, the answer would be 0. So simply by rotating the loop, I'm creating a change in magnetic field. In this case, it's decreasing, decreasing, decreasing until it's 0, and then it's increasing, increasing, increasing again until it's a maximum value. If I keep on rotating it, this is going to be a constant change in flux, which means I end up creating electricity going one way, then the other way, then one way, then the other way as it goes around and around. And that's actually what we call a generator. Okay? The fact is, in this case over here, overall, when it's perfectly horizontal, we have the maximum amount of flux, but when it's perfectly vertical, we have 0 flux. Okay, so when it's perfectly vertical, in this case over here, we have 0 flux. And the fact is, we constantly have a current being produced in one direction or the other as it's rotating back and forth. So whenever you talk about power plants, the fact is all power plants generate electricity by simply rotating a loop inside a giant magnetic field.